Welcome to Calculus. Day 1, we're going to look at the average and instantaneous velocity. So the first thing we're going to take a look at is how do we measure speed. We're going to do that using tables, using graphs, and then we're going to take a look at how to move to a more formal definition of the instantaneous velocity. So first, using tables. The table below represents the position of an object as a function of time. I'm going to label the table the independent variable time. T is in seconds, and the position we often refer to as S of t, and that is in meters. Okay, so what is the object's position at time t equals 3 seconds? Well, looking in the table, we see that at time t equals 3 seconds, that S of 3 is 9 meters. What is the total change in the object's position from time 3 seconds to 3.3 seconds? So what we're looking at here is a difference, S of 3.3 minus S of 3. Pulling those numbers from the table, we get 10.89 minus 9 for a difference of 1.89 meters. Okay, when we want to find the average rate of change in the object's position over time, and using that same time interval, we're looking at the total change, S of 3.3 minus S of 3, divided by 3.3 minus 3. So we're going to get our 1.89 meters in 0.3 seconds. Doing a little mental math on that, that's the same as 18.9 divided by 3, moving the decimal place 1 unit. Right, or 6.3 meters per second. All right, you may recognize that calculation as a change in position over change in time, or change in y value over change in x value, right? So we refer to that as the average velocity but that calculation is also just the slope. And we're going to be more specific, the slope of a secant. It's the slope between the 2 points. Okay, taking a look at number 5, the instantaneous rate of change in the object's position at time t equals 3. So here we're not looking at an interval from 3 to 3.3, but we are looking specifically at 3 seconds. We want to know what the slope is right at 3. All right, so we're going to estimate this because right now that's the only way we can do this. All right, so the instantaneous rate of change, sometimes people abbreviate that as IROC. Like they talk about this one as AROC. Okay, so what we're going to do is we're going to take a look at an interval surrounding 3 seconds, using the point just before 3 and just after 3, or just to the left and just to the right. So we're going to take a look at S of 3.1 minus S of 2.9. And the change in time, 3.1 minus 2.9. All right, so pulling those numbers off the table, 9.61 minus 8.41, and the change in time is 0.2 seconds. Simplifying, we're going to get 1.2 meters in 0.2 seconds, which turns out to be 6 meters per second. So we're going to estimate that the instantaneous rate of change right at 3 seconds is 6 meters per second. All right, we call this an instantaneous velocity. Okay, and just like we referred to the average velocity as the slope of the secant, our instantaneous velocity is also referred to as the slope of the tangent. So we'll take a look at those graphically and see what that looks like. All right, it says find 2 other reasonable estimates for the object's velocity at time t. Well, one way to do that is to take a look, perhaps just using the point on the left and 3, or the point on the right and 3. So we could do s of 3 minus s of 2.9 over that change in time interval, which would just be 0.1 seconds. Okay, this is going to be 9 minus 8.41 over 0.1, or 0.59 divided by 0.1, or 5.9 meters per second. So we can see that's pretty close to 6. All right, we could also look at, so I'm going to call this the interval, using the interval on the left. But we could also use an interval on the right and look at s of 3.1 minus s of 3 divided by 0.1. Okay, pulling those numbers off the table, that's 9.61 minus 9 divided by 0.1, or 0.61 divided by 0.1, and that's 6.1 meters per second. Again, very close to 6, our estimate for the instantaneous at 3. So which one do we like the best? All right, our best estimate uses an interval surrounding 3s of 3. So we really like this as the best. All right, but notice if we actually average the left and right hand estimates, we'll end up with an average of 6 meters per second. Okay, so the best estimate uses an interval surrounding the point 3s of 3. Okay, let's move along. All right, so we've just looked at tables, and now we're going to look at graphs. All right. So in this graph, it says we have an object's position in feet, and on the y-axis, and hours since noon on the x-axis, or the time axis. So this is noon, time in hours, and position, s of t, is in feet. and this is distance. Okay, so it says, does the object cover a greater distance over the 2-hour time interval between noon and 2 o'clock, or between 4 o'clock and 6 o'clock? So our first time interval is from noon to 2, and it looks like it started at a distance of 0, and we don't know the y scale, but it appears to be 1, 2, 3, 4, 5, maybe 6 units. Maybe it's 6 1/4. Okay, so on the interval from, I'm going to use interval notation, from 0 to 2, we have 6 1/4 units on the grid. I don't know what those units are, but 6 1/4 units on the grid. If I look between 4 and 6, maybe it looks like we only have 2 units on the grid. All right, so for t between 4 and 6, we have 2 units on the grid. So the greater distance is going to be over this interval. Okay. All right, so that's kind of looking at total change or change, right? Change between time 0 and time 2. In this next question, we want to look at average velocity over those 2 time intervals. So again, average velocity, that's like our change in position over change in time. Now both of these intervals are 2-hour intervals. So on the interval from 0 to 2, we're looking at 6 1/4 units divided by 2 hours. Okay? Or we're looking at 2 units over 2 hours. Okay, well, again, when you're traveling the greater distance over the same time interval, this is going to give you a greater average velocity, right? Okay, is the object traveling faster at 1 p.m. or 4 p.m.? So let's take a look at 1 p.m. This is actually asking us at a specific time. Right? We're not trying to take a look at an average velocity, we're trying to take a look at an instantaneous velocity. So at 1 o'clock, if I attempt to draw a tangent line, which is a little tough to do using my tablet here, but I can see that the slope is steeper at 1 o'clock than at 4 p.m. Okay, so the object must be traveling faster at 1 p.m. Okay, I'm going to stop this video now because my video can only be 15 minutes and I'm at 14 and a half. And I will pick up in part 2 with this next question.